we now want to show you how to evaluate the electric field of a continuous region of charge. So let's look at this example here. Let's say that this is a metal bar of some type and I've just placed a lot of positive charge on it, and those positive charges are going to range themselves so that they are as far apart away from each other as possible, and we can consider this as a uniform distribution of charge if I placed enough charge on there. Now, the way we calculate the electric field is dE, the differential element of the electric field at the point I want to evaluate the electric field at, is equal to Coulomb's constant times the infinitesimal amount of charge to be considered divided by the distance between my point and that infinitesimal point of charge. So let's break this down just a little bit. dE is your infinitesimal amount of electric field at the point, and I'm going to evaluate the electric field due to this continuous region of charge at the origin. Okay, I'm going to evaluate this at the origin. And I'm going to assume that this rod is uniformly charged. Okay. So if I want to get the total electric field, what I need to do is integrate both sides. So how do I actually carry out this integration? So suppose that I'm at the origin and this is the point that I want to evaluate. I want to evaluate the field at this point P, right, which is the origin. One trick that we can employ is to define a new variable, and we call this variable lambda. We call this the charge per unit length. Okay, it's the charge per unit length. So whatever my total charge capital Q is, say I have capital Q on my rod, the lambda is going to be the total charge capital Q divided by the length, in this case 10 centimeters, right? So my rod stretches a length of 10 centimeters. But we're talking about differential elements here. So dE is going to be a differential element, as is dQ. So here's what this equation is saying. Suppose that I break my rod up into several little segments, and this is one segment that I look at. So this segment right here. That segment contains a differential element of the total charge dQ. And this element is also a distance x from the point that I want to evaluate the field at. Okay, so this is the distance from the point that I am looking at to the point that I'm evaluating the field at. And what we do is we essentially consider, once I break up my rod or whatever the shape my object is into these infinitesimally small boxes, that those boxes now act like point charges. So what I'm going to do is I'm going to take each individual tiny box, and this formula, K dQ over x squared, is going to be the electric field at each individual box, and then I add them up and I get the total field dE. So how can I actually write dQ using this new term lambda into something that I can get integration with? Well, if lambda is the total charge per unit length, lambda must also equal the infinitesimal amount of charge on my rod at this point divided by its differential length dx. Okay, so this little box has an infinitesimally small width dx, and it has an infinitesimally small amount of charge on it dq, and the ratio of that dq to this width dx must be the same as the total length q, or I'm sorry, the total charge q to the total length of 10 centimeters, okay? So we can use lambda is equal to dq dx, and what that allows me to do is write dq in a form that I can now integrate. So now that I have dq in this form, I now have a differential with a variable of that integration variable. So this is my integration variable, and here's the integration variable in my integral. So now I can substitute lambda dx in, and I can actually integrate this expression. So now I can integrate this expression, but what are my limits of integration? Well, on the left-hand side, the limits of my integration are just going to go from 0 to the total electric field, okay? So this is essentially just going to go to the electric field E. But what about my limits on this side? Well, the limits of your integration are along the entire length of the rod, okay? So your limits of integration are along the length of the rod, but they start at the distance from the point you're measuring from and go along the rod to your end point. So if the beginning of the rod is at the point 5 centimeters, my first limit is going to be 5 centimeters. And then I'm going to integrate along the rod to this 15 centimeters. So the difference between these two limits should equal the length of the rod. And now I can pull my constants out front. And I've arrived at this expression. So k times lambda times my integrated variable, negative 1 over x, from my endpoints. And I finally arrive at this expression. Now, to go any further, I would need to find common denominators here, which that wouldn't be hard, but that's just algebra. If I wanted to know what the total charge was, or the total field was, I would have to know what my total Q was. So let's say that my total Q just happens to be 1 coulomb. Okay? So my total charge just happens to be 1 coulomb. What is the total field now? And let's do this math real quick, right? So to get common denominators, multiply by 3 over 3, and I get 15. So negative 1/15 and 2/15. And now I can write, okay, I can write lambda as my total charge over my total length. And notice, okay, that this is going to have the units of the electric field because this is technically in 1 over centimeters, and this has units of charge, and this is also unit of length, so I have charge over length squared. And that is what the units on my electric field are, charge over length squared. And remember, this is 1 coulomb, so we can just say 1 coulomb. And then I have K times 1 coulomb times 2 over 10 centimeters times 15 centimeters, which is 150 centimeters squared, and this turns into 2K over 150, or if you wanted, that would be 1 over 75. And the units here are going to be Newton, or well, the units are going to be coulombs per cubic or square centimeter rather. Okay, but that is how you can carry out this integration. Okay, so it depends on what Q is as to how much total charge you have on your rod or whatever shape you have. But the integration itself is the important thing, okay? The integration itself is the important thing. The things to remember are, you always start with this equation, dE equals K times dQ over X squared. And you can define your charge per unit length if you're talking about a one-dimensional rod, which we are. If you were in 2 dimensions, you would need a charge per unit area. If you're in 3 dimensions, you need a charge per unit volume, okay? And then you can always use the definition charge per unit length, charge per unit area, or charge per unit volume to write your dQ in terms of your differential and your proportionality constant, right? And that's what we've done here, and then insert that into this equation. And then the last thing to remember is that your units or your limits of integration need to be along the length of the rod. So the difference between your limits here should be what the length of that object is. All right, hope you found this helpful, and we will see you next time.